Dear viewers, good day to all. In this video, we are going to see mechanics of finite element analysis and key component of finite element analysis. Those are stresses, strains, forces, stiffness matrix, displacements, strain, displacement matrix, and stress strain matrix. In mechanics and physics, stress refer to the force per unit area that acts on a material or structure when subjected to an external load or force. Stress is a measure of the internal forces that develop within a material in response to an external load. Stress can be categorized in several types, including tensile stress, compressive stress, and shear stress. Tensile stress is the stress that develops when an object is pulled, while compressive stress is the stress that develops when an object is compressed. Shear stress is the stress that develops when two forces act in opposite direction parallel to a surface. Stress is an important factor in the analysis and design of structures and material. By measuring the stress of the material, engineers can determine its strength and toughness and calculate the load that it can withstand without deforming or failing. Stress can be measured using various techniques such as strain gauges, load cells, and pressure sensors. In mechanics of FEA, strain refers to the degree to which an object is deformed or destroyed when subjected to an external force or load. Strain is a measure of the amount of deformation per unit of original length, and it is typically expressed as a percentage or decimal value. Strain is a dimensionless quantity, meaning that it has no unit. Strain can be categorized into several types, including axial strain, shear strain, and volumetric strain. Axial strain is the elongation or compression of an object in the direction of an applied force, while shear stress is the deformation that occurs when two forces act in opposite direction parallel to a surface. Volumetric strain is the change in volume of an object due to change in pressure. Strain is an important factor in the analysis and design of structures and materials. By measuring the strain of a material, engineers can determine its stiffness and strength and calculate the stress that can be withstand without deformation or failing. Strain can be measured using various techniques such as strain gauges, optical interferometry, and digital image correlation. Next, force are physical influences that cause a change in the motion or shape of an object. Force can be categorized as either contact forces or non-contact forces. Contact forces are those that require physical contact between two objects, such as friction, tension, or normal force. Non-contact forces, on other hand, can act an object without physical contact, such as gravitational forces, electric force, and magnetic force. Force are measured in unit of Newton or pound. In mechanics and physics, displacement refers to the change in position or location of an object or particle. with respect to its initial position. Displacement is a vector quantity, meaning that it has both magnitude and direction. Magnitude means the distance between the initial and final position. Direction, the straight line distance and direction from the initial to final position. Displacement can be measured in any unit of length such as meters, feet or kilometers. It is often used to describe the motion of the object, particles or fluid in particular direction such as horizontal or vertical displacement. Displacement can also be described as positive or negative depending on the direction of the movement. In engineering, displacement is an key factor in the analysis and design of structures and systems. By measuring the displacement of structure or component, engineers can determine its deformation and calculate its stresses and strain. This information is critical assessing the safety, reliability of a structure or system and in optimization its performance. Stiffness is the ability of an object to resist deformation under an applied force. It is a measure of how much force is required to produce a given amount of deformation or displacement in an object. The stiffer the object, the more force it can withstand without bending, stretching or compressing. Stiffness is commonly used in engineering, particularly in the design of structures and material to ensure that the object can support the load or force it is subjected to without more deformation or failure. Stiffness is usually expressed in unit of force per unit of deformation such as Newton per meter. In engineering and mechanics, the stiffness matrix is a mathematical representation of the stiffness of a structure or a system. It is a square matrix that related to the applied load to the resulting deformation or displacement of the system. The stiffness matrix is used to solve linear equations that describe the behavior of the system under external loads. The stiffness matrix is particularly calculated by analyzing the individual stiffness of each element or component of a structure and then assembling them into a larger matrix that represents the stiffness of the entire system. The stiffness matrix can be calculated for a wide range of structures including beams, trusses, frames and cells. The stiffness matrix is a key tool in the design and analysis of a structure as it provides a way to predict the response of the system to external loads and to optimize its performance. The stiffness matrix is commonly used in the finite element analysis, a numerical method used to solve complex engineering problems. In FEA, strain displacement matrix is a mathematical tool used to relate the strain in a numerical to the displacement of the material. It is a matrix that describes the relation between the local deformation or strain in an object and the corresponding displacement or movement of the object. The strain displacement matrix is typically used in the context of linear elasticity, which assumes that the relationship between stress and strain in a material is linear. The strain displacement matrix is a key component in the formulation of finite element method, a numerical technique used to solve complex engineering problem. It is used to transform the local strain and displacement of an object into a global set of equations that can be solved using matrix algebra. The strain displacement matrix is typically derived from the strain displacement relation of the individual elements or component of a structure, and then assembled into a larger matrix that represents the behavior of the entire system. The matrix is often expressed in terms of displacement gradient, which are the rate of change of the displacement with respect to position. The strain displacement matrix is an essential tool for engineers and scientists working in fields such as civil, mechanical and aerospace engineering, as it allows them to predict the behavior of the material structures under various conditions. In FEA, stress-strain matrix is a mathematical tool used to describe the relationship between stress and strain in a material. It is a square matrix that related the stress and strain in a material under external load or forces. The stress-strain matrix is used in the context of linear elasticity, which assumes that relationship between stress and strain in a material is linear. The stress-strain matrix is an essential tool for engineers and scientists working in the field such as civil, mechanical, aeronautical, as it allows them to predict the behavior of the material and structures under various conditions. The matrix is derived from the stress-strain relationship of a individual element or component of a structure and then assembled into a larger matrix that represents the behavior of the entire system. Stress-strain matrix is often expressed in terms of a material constant such as the Young's modulus, Poisson ratio and shear modulus, which describe the mechanical property of the material. These constants are typically measured experimentally and are used to predict the behavior of the material under different load conditions. The stress-strain matrix is used in a variety of applications such as in the design of structures, the analysis of materials, and the development of new material with specific properties. It is an essential tool for understanding the behavior of the material and structures under various conditions and for optimization their performance. I hope you found this video helpful. Thank you for watching.